Yes, welcome to the physics video lecture once again. Fluid mechanics, video lecture 5. Okay, last time we just did about 4 hours worth in one, so there are pros and cons to that approach, but we went through a lot of vector calculus, vector differentiation, vector analysis. And you could take what we had there last time and expand it to as broad as you want. It's basically the content of Griffith's first chapter electrodynamics book, along with some other stuff. Be that as it may, we're going to make use of it. We also did a little bit of thermo, and the result of that was that we were able to formulate Eulers' equation a little bit differently. So we have Eulers' equation looking like it did before, v dot gradient v. But now instead of, well, just write, we have minus the gradient of the enthalpy, and where gradient W is equal to 1 over rho gradient of pressure. Okay, so that's going to be useful for us immediately. Good, so that's Eulers' equation. And let's now make use of one of our identities that we had derived the other day, or at least I wrote them down. You guys can derive them all in your good time. So from the gradient of A dot B, where A dot B we're going to take as V dot into itself, which is of course V squared, we have, and I'll write down what we then have, we end up with 1/2 gradient of V squared equals V cross the curl of V plus minus, no, where are we? Plus V dot gradient V. So what we could do here, and by the way, this formula was symmetric in A and B because A equals A times B equals B times B. Okay, so we just had 2 of these terms and take 1 of each and divide by 2. Okay. But what we want to substitute is this one. Okay. That's the one we recognize. So we make that substitution in this equation, in Eulers' equation, and we now have dV dt plus. So that V dot gradient of V is now equal to 1/2 gradient V squared minus V cross curl of V. So that's what we can plug in there. So plus 1/2 gradient of V squared minus V cross curl of V. Okay. Equals minus gradient, or W there. Now, here we have obtained this gradient expression here of V squared, so we're going to bring that under the gradient, and now we will have dV dt minus V cross curl of V equals minus the gradient, and then of this W plus 1/2 V squared. As I said before, we couldn't have done that, bring something under the gradient, if we hadn't gotten this in that form there. Okay, so that's another form of Eulers' equation. We want to do 2 things with this. First, we're going to take the curl of both sides. And this is a formal development. So yeah, I'll go ahead and put a box around here. This is just an equivalent version, right, equivalent form of Euler's equation, take the curl of both sides. What that does is it kills the right side because curl of gradient is identically equal to 0. And then we actually get something pretty complicated on this side. So we take the curl of both sides we have, and then we can exchange the time and the spatial derivatives. We allow ourselves that. So we have d dt of the curl of v, and then we'll bring this to the other side. This one was killed, equals the curl of v cross the curl of v. Okay. So after you write that down, you look at it and you think, well, I hope I never have to do that. That's quite a bit of differentiation. But this is a differential equation for what's referred to as the vorticity. So you think of curl of v as a certain quantity and it's of interest in its own right. What one has gained from this formally, and that'll have its practical applications as well, is that there are 3 equations for 3 unknowns here. So you've gotten rid of the pressure that we originally had, which was a 4th quantity, and if you can solve this differential equation, you have the flow, 3 equations, 3 unknowns, and you're not even requiring it to be incompressible. Okay. So let's go ahead and just put that as a note here. Note 3 equations for v, which means in principle it can be solved. And if you do solve it, then you can go back to the original Euler's equation, because now you know v, and you can just plug this back in, and then your only unknown is p. Okay. Or you can go back into the original Euler's equation and solve for p. Because the density, which you'd also need, is actually just a function of position independent of that gradient of p if you go back into here. So I'll just put that as a note, 3 equations for v. Then use Euler to solve for pressure P. Good. Now here's another interesting application. That was just for thoroughness, so to speak. The next thing we want to do is consider streamlines. Actually, back up a moment. Consider steady flows, and then we can talk about streamlines. So a steady flow, V, is V of position, but not V of time. Okay. So a steady flow you can just think of as a time-independent vector field, which means that dV dt, just like in fluid statics, by the way, which we already talked about, dV dt is equal to 0, the partial, and then we'll go ahead and look at this equation here again. Okay, and since dV dt is equal to 0, we now have V cross curl of V is equal to the gradient W plus 1 half V squared. So now that's our differential equation. And this idea of streamlines brings a big simplification in. So I should say something about streamlines. First of all, this is now, like I said, a steady flow, so we just have a time-independent vector field. And you guys are familiar with vector fields. And a streamline is what we're used to thinking of as a field line, if we have a vector field. So let's say something about streamlines here. Streamlines are tangent to the vector field, the velocity field B. B. So yeah, I'll even put here parenthetically field lines because we've heard about that before. And how are these characterized? The differential equation or the condition that characterizes them is the following. So you could say you've got dx over bx equals dy over by equals dz over vz, where your vx, y, and z are, of course, your components of the vector. Dx, dy, and dz would be the differentials along the streamline. Okay. And just to give you an example, so this is 3 equations in total, this one, that one, and the outside. And so if you just say, what's dy over dx, example dy over dx is just equal to vy over vx, and if you're in the xy plane, then, you know, say you have some fields, some streamlines that are going like that. It's pretty stream-like. You know, then your dy over dx and your vy over vx. There's your vector. You'll even get another color here. Your dy over your dx. Okay. So that's just in keeping with how we think about these things. So, do I have anything else about streamlines? Good. Okay, so far so good. Okay, now continuing, now that we have a definition of streamlines and kind of clear what they are, then let's look at the differential equation again. And so here we are. The streamline, because this is a cross product, the streamline is always perpendicular, right? Because V is perpendicular to this expression itself, okay? Well, V is perpendicular to this cross product, okay? Therefore, the streamline is perpendicular to the cross product at any given point. So that is the important point here. Note that V is perpendicular to V cross curl of V, just by the definition of the cross product. And so streamline is perpendicular to V cross curl of V. And so what that means is, if we let L hat be parallel to a streamline, so L hat is equal to, you know, V over V. I've got a unit vector at some point. Then if I dot this L hat into this expression, then I get left side here, V cross curl of V dotted into this L hat, which is just a vector along the streamline, a little red arrow. That's going to be equal to 0, okay. Which means the gradient of this W plus V squared over 2 dotted into L hat must also be 0. Okay. So this just by the property of the cross product, and this by the fact that we had an equation. Okay. So now, we just have to recognize this thing as the directional derivative. Directional derivative. And depending on what nomenclature you're familiar with for the directional derivative, I think I have a couple of different versions here. So d over dl vector f of r is equal to gradient f of r dot L. Okay, so that's one way to look at it. Another way I have is this one's good too. Limit tau, which is a little scalar, going to 0. Do I have this as a, yeah, d tau f of r plus tau times that little unit vector. Same thing. Then you're going to have your gradient f of r dotted into this L hat. Okay. So that's just a chain rule. You know what? Go ahead and prove homework. Just leave a few lines and work through this to make sure you understand it. Okay. It's actually quite elementary, so it's just a one-liner. So leave a little room in your notes. So once you recognize this as the directional derivative, we have something really interesting. The argument here is constant along a streamline. I'll just make sure I've said enough there. Yes. So the directional derivative along a streamline is constant. I'll send me something. Write that down. So with that, we actually inherit a really powerful equation. So the directional derivative along a streamline vanishes and that means that our expression w plus v squared over 2 is constant along a streamline. And this is Bernoullis' equation right here. We'll obtain a somewhat stronger version of Bernoullis' equation that requires some more stipulations. But right now we have this expression constant along a streamline, and we're going to work with this. So I'm going to expand this back to what it was before. So, oh yeah, let's go ahead and write Bernoullis' equation here. There are a couple versions of Bernoullis' equation, but this is the most general. Okay. And yeah, I'm just going to generalize this. If we have gravity so that g is equal to, and we'll use the z-axis, minus g Z hat, then we can build that into there. Then we can make that substitution. P over rho plus GZ if we want to as well. And all right, and density is constant. Then we can get P over rho plus V squared over 2 plus G times Z. Actually, but be careful there with the sign. No, the sign's good. Is equal to constant as well. Actually, the minus sign is right, because if we were in Eulers' equation, do we have any Eulers' equation up here? We would have had the minus gradient P over rho plus G, so that extra minus sign brings it right into here. Good, so this is the Bernoullis equation that you have in your Physics 4A textbook. Or it's often written this way: P P1 plus 1/2 rho V1 squared plus rho G. Z sub 1 is the same thing since it's constant with the subscript 2. So P sub 2 plus 1/2 rho V2 squared plus rho G Z2. And in this form, it really looks like conservation of energy, and you're just, you're looking at a kinetic and a potential energy type of term. And in fact, if you just multiply this whole thing by a volume, you can say that the work, pressure times volume gives work. The work on a certain fluid along a streamline is equal to the change in its total energy. So that, I may even do that little derivation just to bring it into play. Because if you look up this derivation of Bernoullis' equation, make sure we have that there, then you'll see in your lower division book they do kind of a quick energy conservation argument, and they don't really discuss the streamline, but here we did it completely formally, and so we have this, not some kind of hand-waving argument, but the real thing. Okay, so I want to do a few applications of Bernoullis' equation, just in case you haven't seen them before. Right, so like I said, it looks like energy conservation, or work energy. Actually, I think right under here I'm going to do that little derivation from the lower division text. I think I have it here somewhere. I'll put this as a note. Right, it looks like energy conservation. Here's what we'll say. Note, if you start with P, let's see here. pressure times volume. So if you have P times delta V, you know that's force per area times delta X. So you have P1 delta V1. Force per area delta X. That's work, right? F delta X is a delta W, we'll just even write work. And you do that on each of these two pressures. Bring it to one side, that's the difference in the work along a streamline. And then these would be the differences in the kinetic plus potential energy. So it's the difference in the total energy of a fluid element along a streamline is how the derivation comes in your Physics 4A book to get this equation here. But we're just going to work with this now a couple times, a couple examples. So this we'll just call examples of Bernoullis equation. This kind of thing we should all have seen. Didn't see it the first time around, you'll see it now. So Bernoullis equation, examples and applications. I have a bunch of them, but we'll just do a couple. Examples and applications. So we're along a streamline, and the first thing we'll do is go back to our idea of a constriction. So we got a flow and a constriction, and we're going along a streamline here, right down the middle. And it's pretty clear that V1 is smaller than V2 in the constriction here. And notice we're also on the horizontal, so we've got a horizontal flow. And that allows us to write Bernoullis equation here as P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. So what we get from this immediately is that where the speed is smaller, the pressure must be larger, and vice versa. So we have a lower pressure when the speed is higher. Okay. So immediately with the constriction, we have higher pressure, lower speed, higher speed, V, lower pressure, P. So that's one interesting application there. And if you just hold, you guys can do this at home. If you just hold two sheets of paper, I'll get the two sheets of paper. I'm just going to tell you what to do. You guys try it, then you'll be surprised. So if you just hold two sheets of paper vertically, this separation, and then blow between them, try it and see what happens. Okay, so you hold them right here and you blow between them, just like towards the camera here, towards you guys. And what you'll have is a higher airspeed between the sheets of paper and a lower one outside. Okay. So demo, just a recommendation. Everybody should try that. And that has interesting applications for aeronautics as well. but also just, you know, even in weather, the relationship between wind and changing pressure, high pressure, low pressure fronts and stuff. So very general and important expression. The other, the other example. Okay, this other example is just as good. So imagine you have a big water tank and you shoot a little bullet hole in the bottom and the tank is like that, okay? So we'll just call this a water tank. And I'll make the depth of this thing simply be h here. And the idea is that we have water shooting out horizontally, right? And we have water at the surface. And if we can imagine this water coming here via a smooth flow, okay? Smooth flow. What's happening is water's shooting out and the water level is dropping, but it's dropping very slowly because the small hole in the large tank. Okay. So we'll just label these points here, then we have surface 1 and where the water is emerging 2. So with a small hole. And then we take Bernoullis equation. Now we have P1 plus 1/2 rho V1 squared plus rho GZ1, P2 plus 1/2 rho 2 squared plus rho GZ2. And what are the two pressures? Well, the pressure at the top here is atmospheric pressure, and the pressure on the water where it's emerging is also atmospheric pressure. So we have atmospheric pressure, both of these, they go away. Then we have a 1/2 rho V1 squared. This is going to be very small because the speed up here is basically the speed with which the water line is lowering. So small enough to be negligible, and we're just left with these three here, and in particular we'll just solve for V2. So what do we get? We get V2, rho cancels everywhere, is just going to be square root of 2g times that height difference, Z1 minus Z2, which is just h. So I have, I'll go ahead and write it out. Z1 minus Z2. That looks just like the speed that something would acquire falling through that vertical distance, like the law of free fall. It's called Torricelli's theorem. And if you want, of course, you can have a finite size hole and another finite size level up there, and then you would use your continuity equation. And get a more exact value, but as long as the hole is small, this is fine. Okay. There's yet another application. Maybe we should even have done it first, but that's okay. Namely, what if the speeds are both 0? Actually, I should talk about it right here. So I just wrote down Bernoullis equation. So let's look at Bernoullis equation again. So my last example is if the two speeds are equal and 0. That's a legitimate limit of something going very, very slow. And in terms of streamlines, it's really legitimate because streamlines, have to be well defined. They can't cross and have any kind of turbulence in them. So as v goes from smaller and smaller to 0, you definitely have an appropriate limiting case. So finally, I'll write here v1 equals v2 equals 0, and then a closer look at this shows us that we just have the pressure depth formula. Then P equals P0 plus rho G H, the pressure depth formula, or difference of Z if you want as well. I'll just write the H because it's a simple form. Pressure depth, from which we could also continue on and obtain Archimedes' principle and so forth. So pressure depth formula. Okay, I'm going to consult the clock here. It's actually a nice development. Okay. Let me give you another, these are examples and applications. So we have the Torricelli's theorem. Let me just put this as a note. You guys may want to look this up as well. Venturi effect. Venturi effect, Bernoullis effect, that's really along these lines here, okay? When the, higher pressure, lower speed, higher speed, lower pressure. So it's also a method of measuring pressures. If you had, a column of fluid here, the column would be, that's connected to this pipe here, the column would be higher here and lower here. It would be a direct way of measuring the pressure. So yeah, you should put this in your notes, Venturi effect, Venturi meter, and maybe look that up as well. That's another application. Since we made it to the pressure depth formula, I think I'll say a few more things about atmospheric pressure. Good way to round this discussion out. Let's see, there's a bunch of So yeah, let's go ahead and make a little section on atmospheric pressure. This will be another fluid statics discussion. And I didn't bring the demo object, but we're just going to talk about suction cups for a moment. Another great demonstration, if you haven't seen it, you should. I'm just going to describe it. This is something you guys can do at home. You take an empty aluminum soda can and just put a little bit of water in it, and then heat it up with a flame. So oil, you've got maybe a 1/4 inch, doesn't take that much, 1/2 inch of water in the bottom of the soda can. Boil water in the soda can, and then it has to be boiling really well, and so you got a lot of steam coming out. Okay, so you really see that steam bubbling out. And then all you have to do is take the can and invert it into a dish of water. So you grab it with some tongs, invert it, opening down into the dish of water. Okay, the opening's there, so invert. You do this in one smooth move. Invert it into the dish of water. And it will, if you do it right, it will instantly crumple under the atmospheric pressure. Okay, we're not feeling the atmospheric pressure, but just like the suction cup demo, it's really hard to pull them apart. Here, that will just immediately crumple. And you look for some videos online, and people do this experiment, even with some kind of oil drums or something large, and then I think they heated it and spray it with water or something. So it's a dramatic effect, and those are two dramatic examples of atmospheric pressure. Good, so those are your two demonstrations. Next, the barometric pressure, or atmospheric pressure, that's right, barometer. The demo there would be to have a long capillary, and it better be long enough, and you fill it with, all the way to the top, you fill it with mercury, all the way to the top, then you cap it with your thumb and invert it into a dish of mercury. So mercury, you invert it into that dish, and here's what you get. Your capillary suddenly has a vacuum at the top. So I'll just put here vacuum. There's nothing. It stabilizes, even though it was full. You invert it, put it in that dish. Vacuum, and then you argue that the pressure on the fluid outside the capillary, P equals atmospheric pressure, is equal to density G times H of that column. Just the pressure depth formula, except in terms of that column. So P atmospheric equals rho GH. And the reason you have to use mercury is if you used water, that column would have to be roughly 10 meters. Okay. So rho GH, use mercury, and then this H is on the order of 1 meter. And will vary. This is a practical barometer. As atmospheric pressure increases, that column will go up. As it decreases, that column will drop a bit. So that's how you measure your atmospheric pressure. That's your principle of the barometer. So this is homework in the sense that look this up and put it into these notes right here. So if atmospheric pressure is equal to 1.01 times 10 to the 5 Pascal, find H sub mercury. And then find H sub water. with water, it's pretty trivial. Your G is about 10, your rho is about 1,000, so 10 to the 4 or 5. So it's roughly 10 meters. But this is a good place to put those things in there. Okay, I'm going to consult the clock again. Good. Finally, I'll do a little so-called exponential atmosphere discussion. So now that we have this pressure depth formula right back out of fluid mechanics, what about the atmosphere over larger distances? So this one I'm going to call atmospheric pressure exponential atmosphere. Okay, so here we're actually going to use the ideal gas law without any kind of derivation. PV equals N K volts at temperature, and we're going to have a z-axis. There's the surface of the Earth, and we're going to take it to where the density is not constant anymore. Now we're going to have to make an assumption that the temperature is constant to get this simple thing, and of course the temperature decreases with altitude as well. But this is the Kelvin scale, and if you get a couple degrees Kelvin every several hundred meters, then on a scale of 200, 300 degrees, this temperature will remain reasonably constant for several thousand meters. Okay, so that's the justification. All right, T is a constant for several thousand meters. Namely, delta T over 300 is fairly small. Good, so we'll do that assumption, and now we'll just, since we need a pressure formula, P N over volume, K Boltzmann temperature, and there's a number density, and then a mass density will also be of the same proportionality. Good. That means we're going to have pressure and density proportional. Let's see, is that going to, yeah. That means pressure proportional to density. And then we can just turn this pressure depth formula, which is no longer up here, we can turn that into a differential equation. Yeah, that works. So from pressure depth formula, dP dz is equal to minus rho g. Okay. minus sign again because we're measuring positive z in the up direction. And pressure is proportional to density. We'll have that up there. So Vp over P is equal to rho gz, hold on here, P naught dy minus rho g P naught dz, using z, not y. And this we can just integrate up. Okay, so we'll have the natural log in fact natural log P over P0 minus rho g over P0 z, and we have P equals P0 e to the minus rho g P0 times z. So there's an exponential decay of the atmosphere. And again, did I say that T is approximately constant? So this is good for, you know, several thousand meters. Eventually it becomes less accurate. Good. Once more, consult the clock. And good. So we'll call it a day on this. One thing you could do is for Z equals 0, this is atmospheric pressure at sea level. So Z equals 0, P0 at sea level. And then what would this, it would be a question you guys might want to look up. So leave a couple space in your notes. So what we want to know is density of air times G divided by P0 at sea level. Okay. Find density of air G P0 at sea level, and then you can get a feeling for, you know, how fast the pressure and therefore also the density is decreasing. Yeah, these are the values at sea level, because that has to be a constant for us to integrate. We can estimate these though, because we know it's about 10 to the 5. It's about 10 to the 4. No, 10 to the 5. This is about 1/10. Okay, so 10 over 10 to the 5, 10 to the minus 4. There you have it. So around 10,000 meters, you'll be down to about 1 over E, and that's roughly what you have for Mount Everest. So yeah, if you go ahead and look at these, you'll get an idea of how much the pressure decreases. And with that, we'll take it up next time. See you guys later.